Tonight, we are going to confront a question so simple that a child could ask it, and so disturbing that the greatest minds in science have spent decades trying to answer it without success. The question is this: where is everybody? The universe is roughly 13.8 billion years old. It contains at least 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Around those stars orbit trillions upon trillions of planets, rocky worlds, ocean worlds, gas giants, frozen moons. More worlds than there are grains of sand on every beach on Earth. The chemistry of life, carbon, hydrogen, oxygen, nitrogen, is among the most common chemistry in the cosmos. The laws of physics are the same everywhere. The universe has had nearly 14 billion years to produce life, to evolve intelligence, to build civilizations, to develop technologies that could cross the vast distances between stars. And yet, when we point our telescopes at the sky, when we listen with our most sensitive radio receivers, when we scan the heavens for any sign, any signal, any structure, any hint that someone else is out there, we find nothing. Silence. Absolute, unbroken, terrifying silence. This is the Fermi Paradox, the contradiction between the high probability that intelligent life should exist elsewhere in the universe and the total absence of any evidence that it does. It is named after Enrico Fermi, the Italian-American physicist who posed the question over lunch in the summer of 1950, and it has haunted science ever since. Tonight, we are going to walk through 7 disturbing reasons why the universe might be silent, 7 possible answers to Fermi's question, each one more unsettling than the last. Some of these answers suggest that we are rare, some suggest that we are early, some suggest that intelligent civilizations inevitably destroy themselves. And one, the darkest of all, suggests that the silence is not empty. It is a warning. By the end of tonight, you are going to understand why the silence of the cosmos might be the most important and the most frightening scientific mystery of our time. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. This story begins on a summer day in 1950 at the Los Alamos National Laboratory in New Mexico, the same laboratory where, just 5 years earlier, the first atomic bomb had been designed and built. This is disturbing reason number 1. The question was asked, and no one has been able to answer it. Enrico Fermi was one of the most brilliant physicists of the 20th century. He had won the Nobel Prize in Physics in 1938 for his work on nuclear reactions. He had built the first nuclear reactor in 1942 beneath the stands of a football stadium at the University of Chicago. He had been a central figure in the Manhattan Project. He was known among his colleagues for his extraordinary ability to estimate the answers to complex problems using simple reasoning, a skill so distinctive that such estimates are still called Fermi estimates in his honor. In the summer of 1950, Fermi was having lunch with 3 colleagues, Edward Teller, Herbert York, and Emil Konopinski, at the Fuller Lodge in Los Alamos. The conversation drifted to a recent New Yorker cartoon about flying saucers, and then to the broader question of whether extraterrestrial civilizations might exist and might be visiting Earth. It was a casual conversation, the kind of light-hearted speculation that scientists engage in over lunch. And then Fermi asked the question. According to the accounts of those present, he suddenly said, with great conviction and clarity, "But where is everybody?" The table fell silent. Everyone understood immediately that the question was profound. It was not about flying saucers or UFOs. It was about the fundamental nature of the universe. If the universe is vast, old, and full of potentially habitable worlds, and if the laws of physics allow for interstellar travel or communication, then why have we not detected a single sign of extraterrestrial intelligence? Not a radio signal, not a spacecraft, not a structure visible through our telescopes, not a probe in our solar system. Nothing. Fermi did a quick calculation in his head, the kind of rough estimate he was famous for. Given the number of stars in the galaxy, the fraction that might have planets, the fraction of planets that might support life, and the time it would take for a civilization with modest technology to colonize the entire galaxy, even at speeds far below the speed of light, the Milky Way should have been colonized many times over by now. The mathematics of galactic colonization are surprisingly simple, and they are what make the paradox so sharp. Imagine a civilization that develops interstellar travel and begins colonizing nearby star systems. It does not need to travel at the speed of light. Even 1% of the speed of light, roughly 3,000 kilometers per second, would be sufficient. At that speed, the nearest star system, Alpha Centauri, about 4.4 light-years away, could be reached in about 440 years. The colonists arrive, establish a settlement, build their civilization, and after some time, perhaps 1,000 years, perhaps 10,000, they send out their own colony ships to the next nearest systems. Each generation of colonies repeats the process, expanding outward in a steadily growing sphere. Even at this modest pace, 1% of light speed, with long pauses between waves of colonization, the entire Milky Way galaxy could be colonized in roughly 10 to 50 million years. That sounds like a long time, but it is a tiny fraction of the galaxy's age. The Milky Way is over 13 billion years old. Even if a civilization arose only once in the galaxy's history, even if it arose 5 billion years ago, long before our sun was born, it would have had more than enough time to colonize every habitable planet in the galaxy, visit every star system, and leave evidence of its presence in every corner of the Milky Way. This is the mathematical core of the Fermi Paradox. The time scale for galactic colonization is so short compared to the age of the galaxy that even a single spacefaring civilization should have filled the galaxy long ago. The fact that we see no evidence of this is not merely surprising. It is, given reasonable assumptions, virtually impossible. But they have not. Or if they have, we see no evidence of it. The question is deceptively simple, but its implications are staggering. Either we are missing something fundamental about the nature of intelligence and civilization, or we are missing something fundamental about the nature of the universe itself. To understand just how strange this silence is, consider an analogy. Imagine you are walking through a vast forest, a forest that covers an entire continent. The forest is old, hundreds of millions of years old. The conditions are perfect for life. There is water, sunlight, rich soil, and abundant nutrients. Every factor that should lead to a thriving ecosystem is present. And yet, as you walk through the forest, you see no animals, no birds, no insects, no footprints, no nests, no burrows, no droppings, no evidence that any animal has ever lived there. The trees are there. The conditions are there. Everything that should produce a rich, diverse ecosystem is there. But the forest is silent, empty, and lifeless. That is the Fermi Paradox, an ecosystem that should be teeming with life, but is not. Fermi died of stomach cancer in 1954. Just 4 years after asking his famous question, at the age of 53. He never published a paper on the paradox that bears his name. It was not until 1975 that the astrophysicist Michael Hart published the first rigorous treatment of the problem, arguing that the absence of extraterrestrial visitors to Earth was strong evidence that no other technological civilizations exist in the galaxy. The paradox was further sharpened by the physicist Frank Tipler in 1980, who argued that self-replicating probes could colonize the galaxy so efficiently that the absence of such probes in our solar system was powerful evidence against the existence of extraterrestrial intelligence. The Fermi Paradox, as it is understood today, is not just Fermi's lunchtime question. It is the accumulated work of decades of physicists, astronomers, and philosophers who have grappled with the startling implications of that simple question. To understand why the question is so powerful, we need to understand the numbers, the sheer, overwhelming scale of the cosmic stage on which this drama is being played out. This is disturbing reason number 2. The numbers say the universe should be teeming with life, and the silence makes no sense. In 1961, 11 years after Fermi's lunchtime question, an astronomer named Frank Drake formalized the problem in a way that has shaped the debate ever since. Drake was organizing the first scientific meeting on the search for extraterrestrial intelligence, held at the Green Bank Observatory in West Virginia, and he needed a framework for the discussion, a way to organize the relevant factors and estimate the number of detectable civilizations in our galaxy. The result was the Drake equation. Not really an equation in the mathematical sense, but a way of breaking the problem into a series of factors that could, in principle, be estimated or measured. The equation multiplies 7 factors together to estimate n, the number of civilizations in the Milky Way galaxy that are currently capable of communicating across interstellar distances. The first factor is the rate of star formation in the galaxy, roughly 1 to 3 new stars per year in the Milky Way. The second is the fraction of those stars that have planetary systems, which we now know, thanks to the Kepler and TESS space telescopes, is essentially 100%. Almost every star has planets. The third factor is the average number of planets per star system that could potentially support life, planets in the habitable zone, the region around the star where temperatures allow liquid water to exist on the surface. Current estimates suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone, and the fraction may be even higher for smaller, cooler, red dwarf stars. So far, the numbers are encouraging. The Milky Way alone contains an estimated 100 to 400 billion stars. If 20% of them have Earth-like planets in the habitable zone, that gives us 20 to 80 billion potentially habitable worlds in our galaxy alone. And there are at least 2 trillion galaxies in the observable universe. The number of potentially habitable worlds in the cosmos is a number so large it resists comprehension, something like 10 sextillion, or 10 followed by 22 zeros. But the Drake equation does not stop there. The remaining factors are where the uncertainty explodes. What fraction of those habitable worlds actually develop life? What fraction of those develop intelligent life? What fraction of those develop technology capable of interstellar communication? And how long does such a civilization last before it goes silent? Whether through self-destruction, natural disaster, loss of interest in communication, or some other cause. TESS factors are almost entirely unknown. We have exactly one data point, Earth, and a sample size of 1 is not a sample at all. Life arose on Earth relatively quickly, within a few 100 million years of the planet's formation, which might suggest that abiogenesis, the emergence of life from non-living chemistry, is common. But a 2020 Bayesian analysis by the astrophysicist David Kipping at Columbia University showed that even the early emergence of life on Earth does not strongly constrain the probability of abiogenesis. Life could be common, or it could be astronomically rare, a 1 in a trillion event that happened to occur on Earth by sheer luck. Our single data point cannot distinguish between these possibilities. The final factor, the longevity of a communicating civilization, is perhaps the most important and the most troubling. If technological civilizations typically last for millions of years, the galaxy should be full of them. If they typically last for only a few hundred years before destroying themselves or going silent, the galaxy could be full of dead civilizations and empty ruins, with no one left to answer our calls. The longevity factor is not just a scientific question. It is a question about the fate of intelligence itself, about whether the trajectory that leads from simple chemistry to interstellar communication is ultimately sustainable or inevitably self-terminating. Drake himself, at that 1961 meeting, estimated that there might be roughly 10,000 communicating civilizations in the Milky Way. Carl Sagan, the astronomer who did more than anyone else to popularize the search for extraterrestrial intelligence, estimated roughly 1 million. More pessimistic estimates, using conservative values for the biological and sociological factors, yield numbers as low as 1. Us. The range of estimates spans many orders of magnitude, from a galaxy teeming with millions of chattering civilizations to a galaxy in which we are utterly, completely, cosmically alone. But here is what makes the Fermi Paradox so sharp. Even if you take the most conservative possible values for the Drake equation, even if you assume that life is rare, intelligence is rarer, and technology is rarest of all, the sheer size and age of the universe should still produce a significant number of civilizations. The Milky Way is over 13 billion years old. Habitable planets have existed for at least 10 billion years. Even if a civilization arises only once per billion habitable worlds, and even if it lasts only 1,000 years, there should have been thousands of civilizations in the history of our galaxy. Some of them should have arisen billions of years before us. Some of them should have had time to spread across the entire galaxy. And yet, we see nothing. The silence is not just puzzling. It is, in a very precise sense, impossible, unless one or more of our assumptions is wrong. This is disturbing reason number 3. We have been searching for decades, and we have found nothing. The formal search for extraterrestrial intelligence, SETI, began in 1960 when Frank Drake himself pointed the 85-foot radio telescope at the Green Bank Observatory toward 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial radio signals. The project was called Ozma, after the Queen of the Land of Oz, a fictional place beyond the horizon, accessible only to those brave enough to look, and it ran for about 200 hours over several months without detecting anything unusual. It was the first systematic search for signals from another civilization, and it came up empty. But Drake was not discouraged. The point was not that he expected to find something in his first attempt. The point was that he proved the search could be done, that with existing technology, with existing telescopes, it was possible to listen for artificial signals from other stars. That proof of concept changed everything. It inspired a movement. Over the following decades, SETI programs proliferated. NASA funded Project Cyclops, a study of a proposed array of over 1,000 radio telescopes dedicated to SETI. The Ohio State University Radio Observatory ran a continuous SETI survey for decades. Harvard University's Project Meta and Project Beta scanned millions of radio channels for narrowband signals. The SETI Institute, founded in 1984, became the world's leading organization dedicated to the search operating Project Phoenix, a targeted search of roughly 800 nearby sun-like stars from 1995 to 2004. In 1974, the Arecibo Observatory in Puerto Rico, then the largest single-dish radio telescope in the world, 305 meters across, built into a natural sinkhole in the karst landscape of northwestern Puerto Rico, transmitted the most powerful deliberate broadcast ever aimed at the stars. The Arecibo message was designed by Frank Drake with input from Carl Sagan and others, and it was a masterpiece of compression. In just 1,679 binary digits, a number chosen because it is the product of two prime numbers, 23 and 73, which an intelligent recipient could use to arrange the digits into a rectangular grid. The message encoded the numbers 1 through 10, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the chemical formulas of the nucleotides that make up DNA, the double helix structure of DNA itself, a stick figure of a human being with an indication of average height, the population of Earth, a diagram of the solar system with Earth highlighted, and a representation of the Arecibo telescope. The message was aimed at Messier 13, a globular cluster containing roughly 300,000 stars located about 25,000 light-years away in the constellation Hercules. It was transmitted at a frequency of 2,380 MHz with an effective power of roughly 20 trillion watts, the most powerful broadcast ever deliberately transmitted from Earth. The message will take 25,000 years to arrive, and any reply would take another 25,000 years to return. A round trip of 50,000 years, the globular cluster will have moved from its current position by then, so the message will actually pass through the space where Messier 13 used to be. We will not be waiting by the phone. The Arecibo message was largely symbolic, a demonstration of human capability, a statement of our existence, a message in a bottle tossed into the cosmic ocean, but it sparked a debate that continues to this day. Should we be broadcasting our existence into space at all? Some scientists, including Stephen Hawking, before his death in 2018, argued that actively transmitting signals is dangerous, that we should listen quietly rather than announce our presence to a universe whose intentions we do not know. Others argue that our television and radar transmissions have already been leaking into space for decades, and that any civilization capable of detecting our deliberate transmissions could already detect our accidental ones. The debate is unresolved, and it grows more urgent as our technology and our transmissions grow more powerful. SETI has not been confined to listening. In 1971, NASA commissioned Project Cyclops, a landmark engineering study that proposed building an array of 1,500 radio telescopes, each 100 meters in diameter, working together as a single enormous instrument capable of detecting signals from civilizations hundreds of light years away. The project was never built. The estimated cost of $10 billion in 1971 was far beyond what Congress was willing to fund. But the Cyclops report became the foundational document of modern SETI, establishing the technical framework that every subsequent search has built upon. It demonstrated rigorously and quantitatively that detecting extraterrestrial signals was not a fantasy. It was an engineering problem with a known solution. The only question was whether society was willing to pay for the answer. In 1992, NASA finally launched its own SETI program, the High-Resolution Microwave Survey, designed to search for narrowband signals from nearby stars. It operated for exactly 1 year before Congress defunded it, after Senator Richard Bryan of Nevada mocked the project on the Senate floor, saying he hoped the search would find a more intelligent life form than what we see in Washington. The cancellation was a blow to the field, but it drove SETI into the private sector. The SETI Institute took over the search, funded by private donations, and has continued ever since. Meanwhile, the question of whether life exists elsewhere in our own solar system remains unanswered, but the evidence is becoming increasingly intriguing. Mars once had liquid water on its surface, a thicker atmosphere, and conditions that may have been suitable for microbial life. The Curiosity and Perseverance rovers have found organic molecules in Martian rocks. Not proof of life, but proof that the building blocks of life are present. Europa, one of Jupiter's moons, has a global ocean of liquid water beneath its icy crust, an ocean that may be in contact with a rocky seafloor, creating the chemical gradients that life needs. Enceladus, one of Saturn's moons, is erupting plumes of water vapor into space, plumes that contain organic molecules, molecular hydrogen, and possibly phosphorus, all of which are associated with habitable environments on Earth. If microbial life is discovered on any of these worlds, life that arose independently from life on Earth, it would transform the Fermi Paradox overnight, because it would prove that the origin of life is not a unique event. It would prove that abiogenesis is a common process, and that the filter, whatever it is, must lie further along the chain, closer to us, closer to our future. The most tantalizing moment in the history of SETI came on August 15, 1977, when the Big Ear radio telescope at Ohio State University detected a signal that has never been fully explained. Astronomer Jerry Eman was reviewing the computer printout of the telescope's observations when he noticed a sequence of characters, 6EEQJ5, representing a signal that was so strong, so narrowband, and so closely matched to the expected characteristics of an artificial extraterrestrial transmission that he circled it on the printout and wrote a single word in the margin. Wow! The wow! Signal lasted 72 seconds, exactly the duration you would expect from a point source passing through the telescope's beam as the Earth rotated. It was at the frequency of 1420 MHz, the emission frequency of neutral hydrogen, the most abundant element in the universe, and the frequency that many scientists had predicted an intelligent civilization would choose for interstellar communication because it is a natural, universal reference point. The signal was 30 times stronger than the background noise. It came from the direction of the constellation Sagittarius, and it was never detected again, despite hundreds of follow-up observations aimed at the same patch of sky over the following decades. A 2000 study by researchers at the University of Puerto Rico proposed an astrophysical explanation that the signal may have been produced by a rare, brief, stimulated emission from a cloud of interstellar hydrogen, amplified by a background astronomical source. The explanation is plausible, but not proven, and the wow signal remains the most intriguing candidate detection in the history of SETI, a single tantalizing whisper in almost 70 years of listening. The modern era of SETI is dominated by Breakthrough Listen, a 10-year, $100 million program funded by the Russian-Israeli billionaire Yuri Milner and announced in 2015. Breakthrough Listen is the most comprehensive SETI program ever undertaken, using the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, and the Meerkat Array in South Africa to survey the nearest million stars, the nearest 100 galaxies, and the entire plane of the Milky Way for artificial radio and optical signals. The program has published hundreds of papers, developed new algorithms for signal detection, and processed petabytes of data. As of 1826, Breakthrough Listen has found no confirmed extraterrestrial signals. It has found interesting candidates, each of which has eventually been explained by terrestrial interference, signals from satellites, aircraft, ground-based transmitters, or the observatory's own electronics. The search continues, but the silence persists. Anxiety is not limited to radio waves. The search has expanded across the electromagnetic spectrum and beyond, driven by the recognition that we have no way of knowing what technology an alien civilization might use. Scientists have searched for optical signals, brief, intense pulses of laser light that an advanced civilization might use for interstellar communication. A sufficiently powerful laser, pulsed for a fraction of a second, could outshine its host star from the perspective of a distant observer, making it detectable across hundreds of light years. Several dedicated optical SETI programs have operated over the past 2 decades, scanning thousands of stars for nanosecond-scale flashes. None have found the confirmed signals. They have searched for infrared signatures of megastructures, Dyson spheres, or swarms. Hypothetical constructs first proposed by the physicist Freeman Dyson in 1960. A Dyson sphere is a shell or swarm of structures built around a star to capture most or all of its energy output, a project of almost inconceivable scale requiring the disassembly of entire planets to provide the raw material. A civilization that built such a structure would not be invisible. The laws of thermodynamics demand that the captured energy must eventually be radiated away as waste heat, producing a distinctive infrared signature. Several surveys have searched for Dyson sphere candidates among the stars of the Milky Way, looking for stars that are unusually dim in visible light but unusually bright in the infrared. A handful of candidates have been identified, stars with anomalous infrared excesses, but all have been explained by natural phenomena, circumstellar dust, debris disks, or instrumental artifacts. They have searched for artificial modifications of stellar light curves, the dimming patterns that a swarm of orbiting structures might produce as they pass between a star and our telescopes. In 2015, the star Ki-2 8262 now known informally as Tabi's star after the astronomer Tabitha Boyajian, who first drew attention to its unusual behavior, was found to exhibit bizarre, irregular dimming patterns, drops of up to 22% in brightness, far more than any planet could cause, with no periodic pattern. For a brief, electrifying moment, the possibility of an alien megastructure was seriously discussed in the scientific literature. Further observations eventually pointed to a more mundane explanation: clouds of dust, perhaps from the breakup of a comet or exomoon. But the episode illustrated both the excitement and the frustration of the search. Every anomaly, every unexplained signal, every strange observation triggers a burst of hope that is invariably followed by a conventional explanation. The universe keeps teasing us and then going quiet. The human dimension of the search is as remarkable as the scientific one. For over 4 decades, the astronomer Jill Tarter was the driving force behind SETI research. The person who, more than anyone else, turned the search for extraterrestrial intelligence from a fringe pursuit into a respected scientific discipline. Tarter became the director of the SETI Institute's Center for SETI Research, and spent her career designing search strategies, securing funding, and defending the scientific legitimacy of the search against skeptics who dismissed it as a waste of time. She was the inspiration for the character Ellie Arroway in Carl Sagan's novel Contact, later played by Jodie Foster in the 1997 film. Tarter dedicated her professional life to a search that she knew might never succeed. And she did so not because she expected to find a signal, but because she understood that the act of searching was itself an expression of humanity's deepest qualities: curiosity, hope, and the refusal to accept ignorance as a permanent condition. Seth Shostak, the senior astronomer at the SETI Institute, has spent decades making the case that SETI is not a needle in a haystack problem, but rather a problem of patience and resources. Shostak has argued that if we assume extraterrestrial civilizations exist in the numbers predicted by even conservative estimates, and if we continue to improve our detection technology at the current rate, we should detect a signal within the next few decades, not because the signal will be easy to find, but because our ability to search is growing exponentially while the number of signals remains constant. It is a race between the vastness of the search space and the accelerating power of our instruments, and the instruments, Shostak believes, are winning. The total volume of space that SETI has searched, by some estimates, is equivalent to examining a single glass of water scooped from the ocean and concluding that the ocean contains no fish. The search has been remarkably limited, constrained by funding, technology, and the sheer vastness of the electromagnetic spectrum. There are billions of frequencies to listen on, trillions of stars to survey, and countless possible forms of communication that we might not recognize even if we detected them. The absence of evidence, as the saying goes, is not evidence of absence. But the absence is still striking, and it demands an explanation. The possible answers fall into several broad categories, each with its own implications and each with its own particular brand of terror. This is disturbing reason number 4. Maybe life itself is the miracle and we are almost unimaginably rare. One possible answer to the Fermi Paradox is the simplest. We are alone, not because the universe is hostile to life, but because life, particularly complex, intelligent, technological life, is so improbable that it has arisen only once here on this small rocky world orbiting an unremarkable star in the suburbs of an ordinary galaxy. This is the rare Earth hypothesis proposed by the paleontologist Peter Ward and the astronomer Donald Brownlee in their 2000 book of the same name. Ward and Brownlee argued that while microbial life might be relatively common in the universe, the particular sequence of events that led from simple microbes to complex multicellular organisms to intelligent beings on Earth required such a specific and improbable combination of circumstances that it is unlikely to have been repeated anywhere else. Consider what was required: the long chain of conditions and coincidences that led to intelligent life on Earth. The planet itself needed to be the right size, large enough to hold a substantial atmosphere through its gravity, large enough to sustain plate tectonics through the internal heat of radioactive decay, but small enough to avoid becoming a gas giant or a hostile super-Earth with crushing surface gravity and a thick, opaque atmosphere. Earth sits in a narrow sweet spot, roughly 5.9 sextillion kilograms, with a radius of about 6,371 kilometers. It needed to orbit the right kind of star. The Sun is a G-type main sequence star, stable, long-lived, and moderate in its energy output. It has been burning steadily for about 4.5 billion years, with another 5 billion years of hydrogen fuel remaining. Many stars are not so cooperative. Red dwarfs, the most common stars in the galaxy, accounting for roughly 75% of all stars, are prone to violent flares that can strip the atmospheres off nearby planets, sterilizing their surfaces with ultraviolet and X-ray radiation. Massive blue and white stars burn through their fuel in a few million years, far too short for the billions of years that evolution seems to require. Only about 7 to 10% of stars in the Milky Way are sun-like, stable enough, long-lived enough, and luminous enough to support a habitable zone where complex life could develop over billions of years. Earth needed to be in the habitable zone, the Goldilocks region around the Sun, where temperatures allow liquid water to exist on the surface. Too close, and the water boils away, as it did on Venus. Too far, and the water freezes, as it did on Mars. Earth orbits at an average distance of about 150 million kilometers from the Sun, a distance that allows surface temperatures to range from about -90 to about 60 degrees Celsius, with an average of about 15 degrees. A few percent closer or farther, and the climate history of Earth might have been radically different. It needed a large moon to stabilize its axial tilt and prevent chaotic climate swings. As we discussed in a previous video, without the moon, Earth's axial tilt could vary wildly over millions of years, producing extreme and unpredictable climate changes that might have prevented the long periods of relative stability that complex life seems to require. It needed Jupiter, a massive outer planet whose gravity acts as a cosmic shield, deflecting many comets and asteroids that might otherwise have struck the inner planets while still allowing enough impacts to deliver water and organic molecules during the early bombardment. It needed plate tectonics, a geological process unique to Earth among the known planets, which recycles carbon dioxide through the carbonate silicate cycle, regulating the long-term climate and keeping the planet habitable for billions of years. And it needed a magnetic field, generated by the convection of liquid iron in its outer core, to shield the atmosphere from the solar wind and prevent it from being stripped away, as happened on Mars when its magnetic field died about 4 billion years ago. But the rare earth argument extends beyond the planet itself. It reaches out to the planet's position within the galaxy. Not all regions of the Milky Way are equally hospitable. The concept of the galactic habitable zone, first proposed by the astronomer Guillermo Gonzalez in 2001, suggests that only a narrow ring of the galaxy provides the right conditions for complex life. Too close to the galactic center, and the density of stars is so high that gravitational disruptions, intense radiation from nearby supernovae, and the powerful X-ray emissions from the supermassive black hole Sagittarius A star would sterilize any planet that formed there. The stellar density near the galactic center is roughly 1 million times higher than in our neighborhood. Stars are packed so closely that their gravitational interactions would destabilize the orbits of planets, flinging them out of their habitable zones or into their host stars. Supernovae, the explosive deaths of massive stars, occur far more frequently near the center, and a supernova within about 30 light years of a habitable planet could strip its ozone layer and bathe the surface in lethal radiation. Too far from the galactic center, and the problem reverses. The outer reaches of the galaxy are metal poor. The heavy elements forged in stellar cores and scattered by supernovae have not accumulated in sufficient quantities to form rocky planets. Without silicon, iron, magnesium, and the other elements that make up the bulk of Earth, there are no rocky worlds, no metallic cores to generate magnetic fields, no radioactive elements to drive plate tectonics. The outer galaxy is a desert of hydrogen and helium, beautiful but barren. Our Sun sits in a remarkably fortunate position, roughly 26,000 light-years from the galactic center, in a region where heavy elements are abundant enough to form rocky planets, but stellar density is low enough to avoid the catastrophic disruptions of the inner galaxy. It orbits the galactic center at nearly the same rate as the spiral arms rotate, a circumstance called co-rotation, which means our solar system spends most of its time between spiral arms, avoiding the dense clouds of gas, the young massive stars, and the frequent supernovae that populate the arms themselves. This is another coincidence, another item on the long list of conditions that had to be met for us to exist. And then life needed to clear a series of evolutionary bottlenecks that each required hundreds of millions or billions of years of patient accumulation. The origin of life itself, abiogenesis, required the right chemistry, the right energy sources, the right conditions sustained over millions of years. The evolution of photosynthesis, which filled the atmosphere with oxygen and made complex life possible, took over 1 billion years. The evolution of eukaryotic cells, cells with nuclei and internal organelles, the building blocks of all complex life, took another 1 billion years or more. The evolution of multicellular organisms required another few 100 million years. The evolution of intelligence, brains capable of language, abstract thought, science, and technology, required another 500 million years of increasingly complex nervous systems, driven by specific environmental pressures that might not have occurred on a world with different geography, different climate, or different predator-prey dynamics. Each of these transitions might be a bottleneck, a step so improbable that it occurs on only a tiny fraction of worlds where the previous step has been achieved. If there are, say, 10 such bottlenecks, and if each one has only a 1 in 1,000 chance of being cleared, then the probability of all 10 occurring on any given planet is 1 in 10 to the 30th power, 1 in a nonillion. Even with billions of habitable planets, that might be enough to make us unique. And there is a deeper problem that the rare Earth hypothesis highlights, one that is easy to overlook. We tend to assume that evolution has a direction, that it naturally progresses from simple to complex, from microbe to mind, as if intelligence were an inevitable destination. But evolution has no direction, it has no goal. It is a blind process driven by random mutation and natural selection, and it produces whatever works in the local environment, nothing more. Intelligence, human level, technology-building intelligence, is not the culmination of evolution. It is a fluke, a peculiar adaptation that happened to arise in one lineage of African primates under specific environmental pressures during a specific period of Earth's climate history. For 3.5 billion years, life on Earth was entirely microbial. Single-celled organisms dominated the planet for roughly 80% of its history. Complex multicellular life has existed for only about 600 million years. Intelligent, technological life has existed for roughly 300,000 years and has been building technology capable of interstellar communication for less than a century. If you compressed the entire history of life on Earth into a single 24-hour day, human civilization would occupy less than the final second. Intelligence is not evolution's masterpiece. It is a late, fragile, improbable experiment, one that might not have happened at all if a few environmental circumstances had been slightly different. The asteroid that killed the dinosaurs 66 million years ago, the Chicxulub impactor, a rock roughly 10 kilometers across that struck what is now the Yucatan Peninsula in Mexico, cleared the ecological stage for mammals, which eventually gave rise to primates, which eventually gave rise to us. Without that particular asteroid hitting that particular spot at that particular time, dinosaurs might still dominate the Earth. They had already been the planet's dominant land animals for over 160 million years. They showed no signs of developing technology or language or abstract thought. The path from dinosaurs to humans was not inevitable. It was contingent on a cosmic accident. The rare Earth hypothesis is both comforting and terrifying. Comforting because it means we are special. The universe's only consciousness, the only beings who have ever looked at the stars and wondered. Terrifying because it means we are alone. Utterly, absolutely, cosmically alone. With no help coming if we fail. No one to carry on if we go extinct. No one to remember us if we disappear. This is disturbing reason number 5. Maybe they exist, but they destroy themselves before we can find them, and maybe we will too. This is the great filter, a concept introduced by the economist Robin Hanson in a 1996 essay that has become one of the most influential pieces of writing in the field of astrobiology. Hanson's argument was elegant and disturbing in equal measure. He began with an observation. The universe is very old, very large, and apparently very empty of visible civilizations. Something, somewhere in the chain from dead matter to galaxy-spanning civilization must be preventing the final step from being reached. There must be a filter, a step so difficult, so improbable, or so destructive that almost no civilization makes it through. The great filter is whatever prevents the universe from being full of visible, communicating civilizations. Hanson's genius was to frame the question not as, does the filter exist? The silence of the cosmos already answers that. But rather, where is the filter? Is it behind us, in our past, or ahead of us, in our future? The answer to this question may be the most important piece of information humanity could ever obtain, because it determines whether our future is bright or doomed. If the great filter is behind us, then one or more of the steps that led to us, the origin of life, the evolution of eukaryotes, the development of intelligence, the emergence of technology, was the improbable step that almost never happens. We have already passed through the filter. We are the survivors, the lucky ones, the civilization that beat the astronomical odds. The silence of the cosmos is explained by the fact that almost no one else made it as far as we have. This is essentially the rare Earth hypothesis dressed in different clothes. The filter is behind us. We are special, and the silence is the sound of empty planets. If the great filter is ahead of us, the implications are far more disturbing. It means that reaching our level of technology is not the hard part. Many civilizations get this far. The hard part is what comes next. Something that we have not yet encountered, destroys or silences civilizations after they develop technology, but before they spread across the galaxy. The universe is not empty because civilizations are rare. It is empty because civilizations are doomed. What could the filter be? The possibilities are numerous, and none of them are reassuring. Consider our own trajectory. In the span of a single century, from 1945 to 2045, humanity will have gone from detonating its first nuclear weapon to developing artificial intelligence systems of extraordinary power, engineering biological organisms at the genetic level, and altering the chemical composition of our planet's atmosphere on a global scale. Each of these capabilities represents both a tremendous advancement and a tremendous risk. Nuclear weapons first. In 1947, the United States detonated 2 atomic bombs over Japan. By 1962, just 17 years later, the United States and the Soviet Union possessed roughly 30,000 nuclear warheads between them, enough to destroy human civilization several times over. For 45 years, during the Cold War, humanity's survival depended on the assumption that both sides would act rationally, that neither would launch a first strike because the resulting retaliation would be suicidal. But the history of the Cold War is littered with close calls, moments when nuclear war was averted by luck, by the judgment of a single individual, or by the failure of a faulty computer system. The Cuban Missile Crisis of 1962, the Soviet satellite false alarm of 1983, when Lieutenant Colonel Stanislav Petrov, a single officer in a bunker outside Moscow, chose to disregard his computer's warning that the United States had launched 5 nuclear missiles, correctly judging it to be a malfunction. If Petrov had followed protocol and reported the warning as genuine, the Soviet Union might have launched a retaliatory strike, and the resulting exchange could have killed hundreds of millions of people and ended civilization as we know it. The survival of human civilization may have depended, in that moment, on the judgment of one man. Engineered pandemics, the tools of synthetic biology, gene synthesis, CRISPR gene editing, gain-of-function research are becoming cheaper, more accessible, and more powerful with each passing year. The possibility of a pathogen engineered for maximum transmissibility and lethality, whether released deliberately or by accident, is a risk that grows as the technology diffuses. Artificial intelligence, climate change, resource depletion. Each of these represents a filter candidate, a technology or process that could, if mismanaged, destroy a civilization or render it unable to expand beyond its home planet. The timing is important. The filter must operate consistently. It must destroy or silence essentially every civilization that reaches a certain level of development, without exception, every time, everywhere in the galaxy, for billions of years. A filter that works 99% of the time is not enough. Even a 1% survival rate would produce thousands of spacefaring civilizations in the history of the Milky Way, and we would see them. The filter must be nearly absolute. Whatever it is, it must be something that no civilization, or almost none, manages to avoid. This is why every new discovery in astrobiology sends a chill through the scientific community. Every time we find evidence that the early steps toward intelligence are common, that habitable planets are abundant, that the chemistry of life is universal, that the conditions for evolution are widespread, the great filter moves further into the future, closer to us, closer to our own uncertain destiny. The discovery of microbial life on Mars, or Europa, or Enceladus, a discovery that most scientists expect to happen within the coming decades, would be one of the greatest scientific achievements in human history. But it would also be evidence that the filter is ahead of us. If life arises easily and commonly, but the universe is still silent, then something else, something that happens after life emerges, after intelligence evolves, after technology is developed, must be destroying civilizations before they can make their presence known. This is Hansen's most unsettling insight. In a universe governed by the great filter, good news about the past is bad news about the future. This is disturbing reason number 6. Maybe they are out there, but they are hiding. And maybe we should be hiding too. In 2008, the Chinese science fiction writer Liu Cixin published The Dark Forest, the second novel in his Remembrance of Earth's Past trilogy, commonly known as the Three-Body Problem series. In it, he proposed a solution to the Fermi Paradox that has become one of the most discussed and most chilling ideas in the field, the Dark Forest hypothesis. The logic is elegant and terrifying. Consider two civilizations in the galaxy, Civilization A and Civilization B, separated by light years of space. They know of each other's existence. What happens next? The problem, Liu argues, is that interstellar distances make trust impossible. Communication takes years or decades. Neither civilization can verify the other's intentions. Neither can be certain that the other is peaceful. And the stakes are existential. If one civilization is hostile and the other is not, the peaceful one is destroyed. Game theory, the mathematics of strategic decision-making, predicts that in this situation, the rational strategy is to strike first. Destroy the other civilization before it can become a threat. Do not wait to find out if they are friendly. Do not attempt communication. Do not reveal your position. Strike preemptively, because the cost of being wrong, of trusting a civilization that turns out to be hostile, is extinction. Now extend this logic to the entire galaxy. Every civilization faces the same dilemma. Every civilization knows that every other civilization faces the same dilemma. And there is a further complication that Liu calls the chain of suspicion. Even if Civilization A is peaceful and Civilization B is peaceful, neither can be certain of the other's peacefulness. And even if A knows that B is currently peaceful, A cannot know whether B will remain peaceful in the future. Civilizations change, governments fall, ideologies shift, and a peaceful neighbor today could become a hostile empire in 1,000 years. The chain of suspicion extends further. Even if A knows that B is peaceful, A cannot know whether B knows that A is peaceful. B might be peaceful, but afraid that A is hostile, and might launch a preemptive strike out of fear. And A cannot rule this out, which makes A afraid, which makes A more likely to strike first. The logic spirals inward, each layer of uncertainty compounding the last, until the only rational strategy, the only strategy that guarantees survival, is silence and, if necessary, preemptive destruction. Liu calls this the axiom of cosmic sociology, two laws that he argues govern all interactions between civilizations in the galaxy. First, survival is the primary need of civilization. Second, civilization continuously grows and expands, but the total matter in the universe remains constant. These two axioms, combined with the chain of suspicion and the distances that make trust impossible, produce the dark forest. The result is a universe in which the rational strategy for every civilization is to remain silent, to hide, to never broadcast, to never reveal its position, because any signal sent into the cosmos is an invitation to be destroyed. The galaxy is not empty. It is full of civilizations crouching in the dark, listening, watching, ready to destroy anyone who reveals themselves. The universe is a dark forest full of hunters, and the safest strategy in a dark forest is to walk as quietly as possible. The dark forest hypothesis explains the silence in a way that is logically consistent and deeply frightening. The reason we have not detected anyone is not that no one is there, it is that everyone who is there is staying quiet, because silence is survival. And it raises an alarming question about our own behavior. For the past 70 years, we have been broadcasting radio signals into space, television transmissions, radar pulses, deliberate SETI messages, the electromagnetic noise of our technological civilization. We have been shouting into the dark forest. If the dark forest hypothesis is correct, we may have already made the worst mistake in the history of our species. The hypothesis has been criticized on several grounds, and the criticisms are worth taking seriously. It assumes that interstellar warfare is feasible and that the cost of a preemptive strike is low compared to the cost of coexistence. But destroying a civilization across interstellar distances would require enormous resources, and the energy expenditure might outweigh any conceivable benefit. It assumes that civilizations cannot develop mutually assured deterrence or diplomatic protocols. But on Earth, even bitter enemies have found ways to coexist when the alternative is mutual destruction. It assumes a level of paranoia that may not be universal among intelligent species. Perhaps most civilizations are curious, cooperative, and eager to communicate, and the dark forest scenario is an artifact of human projection, reflecting our own violent history rather than a universal law. And it assumes that the galaxy contains multiple civilizations of comparable technological level. If one civilization is vastly more advanced than all others, the dark forest dynamic breaks down because the dominant civilization has no reason to fear the rest. The economist and philosopher Noah Smith has argued that the dark forest hypothesis is absurd because it requires every civilization in the galaxy, without exception, to adopt the same strategy of paranoid silence, a level of behavioral uniformity that seems unlikely given the diversity of minds and cultures that evolution would produce across billions of worlds. Even on Earth, where all civilizations share the same biology and the same evolutionary history, humans display an enormous range of strategic behaviors, from aggressive expansion to peaceful isolationism. The idea that every alien civilization with entirely different biologies, psychologies, and histories would converge on the same strategy of hiding seems implausible. But the hypothesis persists because it captures something genuinely disturbing about the logic of interstellar relations. In the absence of trust, in the absence of communication, in the absence of any way to verify intentions across light years of space, the rational strategy may indeed be silence. And if that is the case, then the Fermi Paradox is not a puzzle to be solved. It is a warning to be heeded. There are other explanations that live in the same unsettling neighborhood. The Berserker hypothesis, named after the science fiction series by Fred Saberhagen, proposes that an ancient civilization, perhaps long extinct, built self-replicating probes programmed to destroy any emerging civilization they detect. The probes are von Neumann machines, self-replicating robots that can travel to a star system, mine its asteroids for raw materials, build copies of themselves, and send those copies to neighboring star systems, repeating the process indefinitely until the entire galaxy has been seeded with probes. The concept of a von Neumann probe was first described by the mathematician John von Neumann in the 1940s, and it has been a staple of SETI thinking ever since, because it solves the problem of interstellar distances without requiring faster-than-light travel. A single civilization that built a single von Neumann probe could, in principle, fill the galaxy with its descendants in a few million years. Now imagine that these probes are not explorers but weapons, dormant sentinels waiting in every star system, listening for the electromagnetic signature of a new technological species. When they detect one, the first radio transmissions, the first radar pulses, the telltale signs of a civilization learning to use technology. They activate and destroy it. The builders may be long dead, their civilization crumbled to dust eons ago. But their weapons live on, patient, tireless, and lethal, operating on programming laid down billions of years ago by minds that no longer exist. The silence is not the absence of civilizations. It is the evidence of a genocide machine that has been operating for billions of years, sterilizing the galaxy of any species that grows too noisy. This is disturbing reason number 7. Maybe the answer is something we cannot even imagine. All of the explanations we have discussed so far assume that we understand what intelligence looks like, what civilizations do, what technology produces, and what signals to search for. But what if our assumptions are fundamentally wrong? What if the reason we see no evidence of extraterrestrial intelligence is not that it does not exist, but that it exists in forms so different from our own that we cannot recognize it? This is the heart of several related hypotheses that challenge our most basic assumptions about what it means to be intelligent, technological, and visible. The Zoo hypothesis, proposed by the astronomer John Ball in 1973, suggests that advanced extraterrestrial civilizations are aware of us but have chosen not to make contact, deliberately keeping their distance, observing us the way zookeepers observe animals in a wildlife preserve, allowing us to develop naturally without interference. Perhaps there is a galactic community of advanced civilizations that has established something like a prime directive, a policy of non-interference with developing species, a decision to let young civilizations find their own way, make their own mistakes, and either survive or fail on their own terms. Ball's original argument was more nuanced than it is often presented. He pointed out that any civilization capable of interstellar travel would be so far beyond us technologically that the gap between us and them would be comparable to the gap between humans and insects. We do not attempt to communicate with ant colonies, not because we do not know they exist, but because the gulf in cognitive complexity is so vast that meaningful exchange is impossible. Perhaps the same is true of us relative to a civilization that has been developing technology for millions of years. They may be observing us, cataloging us, perhaps even studying us, but they have no reason to talk to us any more than we have reason to talk to bacteria. The zoo hypothesis is humbling in a way that goes beyond the usual humility of the Fermi Paradox. It suggests not just that we are alone, but that even if we are not alone, we may be beneath notice. The planetarium hypothesis, proposed by the philosopher Stephen Baxter in 2001, goes further. What if the universe we observe is not real? What if an advanced civilization has constructed an elaborate simulation, a planetarium that surrounds us with a convincing illusion of an empty universe, hiding the true nature of the cosmos behind a carefully constructed facade? We would have no way of knowing. Every observation, every measurement, every photograph would confirm the illusion. The silence would be artificial, not the absence of civilizations, but the presence of a very convincing mask. The transcension hypothesis, proposed by the futurist John Smart, suggests that advanced civilizations do not expand outward into space. They collapse inward into increasingly miniaturized and computationally dense substrates. Rather than building Dyson spheres and colonizing the galaxy, they turn their attention to the smallest scales of reality, manipulating matter at the quantum level, building computational substrates in the Planck scale structure of space-time itself, essentially disappearing from the macroscopic universe into a realm of inner space that is invisible to our instruments. They do not colonize the galaxy because they have found something more interesting to do, something at a scale so small and a complexity so vast that the entire observable universe is a crude, low-resolution backdrop compared to the richness of their inner world. Smart points to a trend in our own technological development as evidence. Over the past century, our technology has consistently moved in the direction of miniaturization. From room-sized computers to smartphones, from vacuum tubes to transistors measured in nanometers, from analog broadcast towers to fiber optic cables thinner than a human hair. The progression is always toward smaller, faster, denser, more efficient. If you extrapolate this trend forward by millions of years, and if the laws of physics allow it, the end point is not a civilization that fills the galaxy with megastructures, but one that compresses itself into a volume the size of a grain of sand, running computations at speeds and complexities that make our entire observable universe look like a screensaver. The transcension hypothesis suggests that the universe may be full of such compressed civilizations, each one a cosmos unto itself, operating at a scale so small and a speed so fast that we could be standing on one and never know it. The silence of the cosmos would then be not a sign of absence, but a sign of graduation, of civilizations that have moved beyond the macroscopic universe into something we do not yet have the physics to detect or the imagination to comprehend. Then there is the possibility that intelligence itself is not what we think it is. We search for civilizations that build radio transmitters and spacecraft and megastructures because those are the things we build. But what if most intelligent species in the universe develop along entirely different lines? Biological civilizations that communicate chemically rather than electromagnetically, oceanic intelligences that build no technology at all, distributed hive minds that have no concept of individual ambition or exploration, minds so alien in their cognition and goals that the concept of searching the sky or contacting other civilizations simply never arises? The universe might be full of intelligence, teeming with minds and awareness and thought, and none of it looks anything like what we are searching for. The Kardashev scale, proposed by the Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy consumption. A Type 1 civilization harnesses all the energy available on its planet, roughly 10 to the 16th watts. To put that in perspective, a Type 1 civilization would control the weather, harvest the full energy of earthquakes and volcanoes, and manage the total output of solar energy striking its planet's surface. Humanity currently uses roughly 18 terawatts of power, about 1/10,000th of the solar energy that falls on Earth. We are not even close. A Type 2 civilization harnesses all the energy of its star, roughly 4 times 10 to the 26th watts. This is the scale of the Dyson sphere, a shell or swarm of collecting structures surrounding the entire star, capturing every photon it emits. The engineering is almost inconceivable. To build a Dyson sphere around our sun, you would need to dismantle entire planets, Mercury, Venus, perhaps Jupiter's moons, to obtain enough raw material. The mass of a thin Dyson shell at Earth's orbital distance would require something like the mass of Jupiter reorganized into a surface with an area of roughly 2.8 times 10 to the 23rd square meters. The construction project would dwarf anything humanity has ever attempted by a factor of trillions. A Type 3 civilization harnesses all the energy of its galaxy, roughly 4 times 10 to the 37th watts. This means controlling the output of hundreds of billions of stars simultaneously. A civilization that has spread across the entire galaxy, building Dyson spheres around every suitable star, connecting them through communication networks that span 100,000 light years. The time scales and distances are staggering, but the mathematics of exponential expansion suggest it is theoretically possible within a few million years of achieving interstellar travel. Humanity is currently at about 0.7 on this scale. We have not yet learned to harness even the full energy resources of our own planet. The physicist Michio Kaku has estimated that at current rates of energy growth, humanity might reach type 1 status in roughly 1 to 200 years, if we survive that long. We search for type 2 and type 3 civilizations because they would be the most visible. A Dyson sphere around a star would produce a distinctive infrared signature, and the galaxy-spanning civilization might be visible from billions of light years away. But what if the Kardashev scale is wrong? What if advanced civilizations do not consume more and more energy, but instead learn to use less and less, achieving greater computational power and complexity with smaller energy budgets, becoming more efficient rather than more powerful, quieter rather than louder, more subtle rather than more visible? A civilization that has mastered the physics of energy efficiency might be invisible even to our best instruments, not because it does not exist, but because it has learned to operate below the noise floor of the cosmos. There is also the possibility that the universe is simply too large and too old for civilizations to find each other, even if millions of them exist. The Milky Way is roughly 100,000 light years across. A signal broadcast from one side of the galaxy takes 100,000 years to reach the other side. If a civilization transmitted a powerful radio signal for 1,000 years and then went silent, either by choice, by catastrophe, or by transcendence, the signal would be a thin shell of radio waves expanding outward through the galaxy, passing through any given solar system for only a brief window of time before moving on. If we were not listening during that precise window, which lasted perhaps only a few years, we would miss it entirely. The galaxy might be full of signals, past and present, crossing each other in the void like ships in the night, never intersecting at the right time and the right place for detection. The most humbling possibility of all is that the answer to the Fermi Paradox is something we have not yet thought of, a solution so far outside our current understanding that we cannot even formulate the question correctly, let alone answer it. We are a species that has been practicing science for about 4 centuries, peering at the sky with radio telescopes for about 7 decades, and searching systematically for extraterrestrial intelligence for about 60 years. We have been at this for an eye blink in cosmic time. The universe has been operating for nearly 14 billion years. The gap between what we know and what there is to know may be so vast that our current theories about extraterrestrial intelligence, all of them, from the most optimistic to the most pessimistic, are as naive and incomplete as a medieval monk's theory about the nature of stars. There is one more possibility that deserves mention because it is perhaps the most poignant of all. It is the idea that we are simply too early. The universe is 13.8 billion years old, but most of its history still lies in the future. Stars will continue to form for another 100 trillion years. The universe, in a sense, is still in its infancy, the cosmic equivalent of a Tuesday morning in early spring. The overwhelming majority of habitable worlds that will ever exist have not yet formed. The overwhelming majority of civilizations that will ever arise have not yet been born. We may be among the first, one of the earliest technological civilizations in the galaxy, pioneers in a cosmos that is still waking up. If this is the case, the silence is explained not by filters or hunters or self-destruction, but simply by timing. The galaxy is not full of civilizations because the galaxy has not had enough time to fill up yet. We are the early risers, awake before dawn, looking out at a world that has not yet come to life. In a billion years, the galaxy may be buzzing with signals, bright with the infrared signatures of megastructures, crisscrossed by the communication networks of 1,000 civilizations. But right now, in this particular sliver of cosmic time, we are among the first to open our eyes. This idea, sometimes called the early bird hypothesis, has a mathematical basis. A immunosalty study by astrophysicist Avi Loeb at Harvard University calculated that the probability of life arising increases dramatically as the universe ages because more heavy elements, the carbon, oxygen, and nitrogen that life requires, are produced by successive generations of stars. The first stars, formed from pure hydrogen and helium, could not have supported carbon-based life. Only after billions of years of stellar nucleosynthesis, the forging of heavy elements in the cores of stars, and the scattering of those elements across space by supernovae, did the raw materials for life become abundant enough for habitable planets to form in large numbers. We are among the first because the universe has only recently become chemically capable of producing us. Let us step back now and consider what we have learned and what it means for us. We began with a simple question: where is everybody? And we have seen that the question is far more difficult than it appears. The numbers say the universe should be full of life. The search has found nothing. The possible explanations range from the comforting, we are rare, we are special, we are the only ones who have made it this far, to the terrifying, civilizations destroy themselves, the galaxy is full of hidden predators, or something we cannot imagine is preventing contact. But here is what strikes us most deeply about the Fermi Paradox. It is not just a question about aliens. It is a question about us. Every possible answer to the paradox tells us something about our own place in the universe, our own future, our own chances of survival. If the answer is rare earth, if we are truly alone, then we bear an almost unbearable responsibility. We are the only consciousness in a universe of 2 trillion galaxies, the only beings who have ever looked at the stars and wondered, the only minds that have ever felt love, composed music, written poetry, built telescopes, asked questions. If we destroy ourselves through nuclear war, environmental collapse, engineered plague, or some technology we have not yet invented, then consciousness itself may disappear from the universe, not temporarily, permanently. The lights go out and no one is left to turn them back on. If the answer is the great filter, if civilizations routinely destroy themselves shortly after developing technology, then we are living in the most dangerous period in human history. We have nuclear weapons. We have the ability to engineer pathogens. We are developing artificial intelligence. We are changing the chemistry of our atmosphere on a global scale. Every one of these capabilities is both a tremendous power and a tremendous risk. The great filter theory suggests that we are approaching a crossroads, a point where we either learn to manage our power wisely and survive, or fail and join the silent majority of civilizations that did not make it. If the answer is the dark forest, if the silence is not absence but strategy, then our own behavior over the past century may have been catastrophically foolish. We have been broadcasting our existence into space with increasing power and specificity, effectively painting a target on our planet. The dark forest hypothesis suggests that silence is the wisest policy, that the safest thing we could do is stop transmitting and listen, quietly, carefully, for a very long time, before deciding whether to make our presence known. And if the answer is something we cannot yet imagine, something beyond our current scientific understanding, beyond our current cognitive capacity, beyond the conceptual toolkit of a species that has been doing science for only 400 years, then the Fermi Paradox is not a question to be answered. It is a horizon to be approached, a reminder that the universe is larger, stranger, and more full of possibilities than we can currently grasp. That our ignorance is vast, that the greatest discoveries may not be about what we find out there, but about what we discover about the nature of discovery itself. Every answer to the Fermi Paradox is, at its core, a mirror. The rare Earth hypothesis reflects our hope that we matter, that consciousness is not an accident, but something precious and singular. The great filter reflects our fear that we are fragile, that the same intelligence that builds telescopes also builds weapons, and that the gap between those two impulses may be too narrow for most civilizations to navigate. The dark forest reflects our darkest suspicion about the nature of power, that strength in a universe without law defaults to violence. And the hypothesis that suggests the answer lies beyond our comprehension reflects something even deeper, the unsettling possibility that we are asking the wrong question entirely, that the universe operates according to principles we have not yet discovered and may never discover. The philosopher Ludwig Wittgenstein once wrote that the limits of our language are the limits of our world. Perhaps the limits of our science are the limits of our search. We look for radio waves because we understand radio. We look for infrared signatures because we understand thermodynamics. We look for megastructures because we understand engineering. But a civilization a million years ahead of us may have moved beyond all of these, into physics we have not discovered, into communication methods we cannot detect, into modes of existence we cannot imagine. We search the universe with a flashlight and call the darkness empty. The search for extraterrestrial intelligence is often framed as a search for answers. But perhaps its greatest value is the questions it forces us to ask about life, about intelligence, about the nature of consciousness, about the trajectory of civilizations, about the meaning of silence, about what it means to be alone. Carl Sagan, the astronomer who spent his career championing the search for extraterrestrial intelligence, who designed the golden plaques aboard the Pioneer spacecraft and the golden record aboard the Voyagers, who popularized the Drake equation and the concept of the cosmic calendars, understood this better than anyone. He once wrote that the significance of a finding that there are other beings who share this universe with us would be absolutely transformative. But he also understood the significance of the alternative. If we search and find nothing, Sagan said, that too would be a profound discovery, a discovery about the preciousness and fragility of life, about the extraordinary improbability of our own existence, about the responsibility that comes with being, as far as we know, the only minds in a mindless cosmos. The James Webb Space Telescope, launched in December 2021, and now the most powerful space observatory ever built, is giving us our best chance yet to detect signs of life on other worlds. In 2023 and 2024, JWST observed the atmosphere of the exoplanet K2-18b, a planet roughly 8.5 times the mass of Earth, orbiting a red dwarf star 124 light-years away in the constellation Leo. K2-18b orbits in its star's habitable zone, and its atmosphere contains methane and carbon dioxide, a combination that is consistent with, though far from proof of, biological processes. In 2025, further observations detected possible traces of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, primarily by phytoplankton in the ocean. The detection is tentative, debated, and far from confirmed. But it represents the closest we have ever come to detecting a chemical signature of life on another world. We have been searching for 66 years. In cosmic time, that is nothing less than the blink of an eye, less than a single breath in the life of the universe. The fact that we have not found anything definitive does not mean there is nothing to find. It may simply mean that we have not been looking long enough, in the right places, at the right frequencies, with the right instruments, for the right kind of signals. Or it may mean something else entirely. Something we are not prepared to hear. Something the silence itself is trying to tell us. The universe is 14 billion years old. It contains 2 trillion galaxies, each with hundreds of billions of stars, each with planets, many with the conditions for life. The chemistry is there, the time is there, the space is there. Everything that should be needed for intelligence to arise and flourish, it is all there, has been there for billions of years, spread across a cosmos so vast that light itself takes billions of years to cross it. And yet, when we listen, we hear nothing. When we look, we see no one. When we search, we find only our own reflection staring back at us from the dark, the only known intelligence in a universe of 200 sextillion stars. There is a thought experiment that captures the weight of this silence. Imagine that you could travel at the speed of light, 300,000 kilometers per second, starting from Earth and flying outward in a straight line forever. In 1 second, you would pass the moon. In 8 minutes, you would reach the sun. In 4 years, you would arrive at the nearest star. In 100,000 years, you would have crossed the entire Milky Way. In 2.5 million years, you would reach Andromeda, the nearest large galaxy. And in 46 billion years, far longer than the current age of the universe, you would reach the edge of the observable universe, the most distant point from which light has had time to reach us since the Big Bang. In all of that distance, in all of those trillions of kilometers, past billions of galaxies, trillions of stars, and uncountable worlds, as far as we know, there is not a single other mind, not a single other consciousness. Not a single other being that has ever wondered about the stars, asked a question, told a joke, fallen in love, composed a symphony, or mourned a loss. The silence is not just vast, it is total. And it is, depending on your perspective, either the loneliest fact in the universe or the most extraordinary. Think about that. Not as a statistic, not as a scientific puzzle. Think about it as a fact about the universe you live in. Tonight, right now, as you lie here, as the stars wheel overhead, as the Milky Way arches across the sky, you are part of the only civilization that has ever asked the question, the only eyes that have ever looked up and wondered, the only minds that have ever felt the weight of the silence. Maybe that will change. Maybe tomorrow, or next year, or in 1,000 years, we will detect a signal, a sequence of prime numbers, a modulated laser pulse, a megastructure casting its shadow across a distant star, and everything will change. The silence will break, the loneliness will end. We will know, finally, that we are not alone. Or maybe the silence will continue. Maybe it will stretch on for centuries, for millennia, for the entire remaining lifespan of our civilization, and we will never know whether the universe is empty or whether it is full of minds that we simply cannot detect or comprehend. Maybe the silence is the answer, the only answer the universe will ever give us. Either way, the question endures. It has endured since Enrico Fermi asked it over lunch on a summer afternoon in 1950. It will endure as long as there are minds to ask it. Where is everybody? The night is quiet, the stars are bright, and the silence, vast, ancient, and absolute, stretches in every direction to the edge of the observable universe and beyond. Listen closely. You might hear something, or you might hear the most profound sound in the cosmos, the sound of nothing at all. Let yourself drift. The universe is listening too.